Okay, enough stalling. Okay, I said there would be AP walkthroughs, here they are. And alright, drum roll, what APs are they gonna be? That's right, AP Calc BC and AP Chem, because those are the two boys that are the hardest ones to me. I personally think that. And also, those are the two that you guys wanted, so that's what you get. Hello everybody, I'm Karara, and basically, I've done a couple calculations, and I'll only be able to cover 2 AP exams fully before the actual AP exam happens, because basically, I'm going to do 1 crash course per unit, and basically, there are 8 units for calc and like 7 units for chemistry, so that basically takes us up to the AP test. Like, before the test, I might do some random AP stuff, but who knows. We're just going to be in AP mode, full AP mode right now. And I'm experimenting here, so I have no idea what works and what doesn't, so right now, I'm going to try to get you as much information as possible, because these AP tests this year are kind of like crazy, because it's just 1 or 2 questions, and you gotta do well on those. So I'm going to throw as much information at you as I can, and hopefully throw in a couple examples, but let me know if you want more examples, you want more explanations, I don't know, you tell me. But today we are doing AP Calc BC Unit 1. It's going to be epic. And basically, AP Calc BC Unit 1 is limits and continuity, which doesn't seem like a very interesting topic, but I think those are the trippiest questions, and I think they could throw them into any single question that you get, so I think it's worth repassing over this. Alright, first things first, limit notations, limits. Okay, you probably should know this if you're taking the test, but I'll just repass it real quick. Alright, so you have lim, and then your variable that you want to find the limit for, then where you want the limit to approach, and then your function, f of x. And basically what this says is what value does f of x approach as you get closer and closer to c. Not at c, but as you get closer to c. So like if the graph of f of x is like this boy, and then there's like a hole there, and then it keeps going, it doesn't matter that there's a hole there, okay? We want to find the limit at, like, let's say this is x is 2. If we want to find the limit at 2, as long as it's approaching the same place from both sides, it doesn't matter if the actual point exists, then the limit is just whatever y coordinate this is, let's say it's 3. So then this is just equal to 3. Very cool. Now remember, it doesn't have to be defined at the point. It just has to approach it from both sides. Now the technical definition is pretty useless, so I'm not going to bore you with that, but if you want to search it up, it's like some random delta and epsilon nonsense that you're not going to use. Alright, so holes are like the easiest limit to deal with because it's literally just what it approaches on both sides. Then, of course, it's asymptotes, right? Where a function just goes like that and like that. Then you can't really define the limit as it approaches, let's say this is like x equals 3. You can't really define the limit as x approaches 3 because it goes to infinity on both sides. But you can basically say it's infinity. Technically it's not defined, but it does go to infinity. So this is x goes to 2, and then lim of x goes to 3 of f of x is going to be equal to infinity. Which technically is not defined, but you can say it's equal to infinity. But what happens if it goes all the way to infinity, okay? Like what happens if your graph like is trolling and it like has something and it approaches some line. Oh, that's not a good drawing. And let's say it goes like this and then it approaches some line and this line is like that. And basically, if we said lim of f of x as x goes to infinity, what would it be? Now we know that it approaches this line. So if this line has y is equal to 1, then this whole thing is going to be equal to 1. However, let's say that at negative infinity just goes like that, then our lim as f of x goes to negative infinity, which means it goes all the way to the left, that we cannot say is a single number because it just increases infinitely. So we could say that it's equal to infinity, which is technically not defined, but it's there. Alright, epic. Now you know how to do it from looking at graphs, okay? But now let's introduce one-sided limits because sometimes it trolls and it's different from both sides. It doesn't approach one single point. So let's say we got our graph over here, and then it's like this, and there's a hole there, and then over here there's another thing here, and it's like that. I don't know, the other stuff doesn't matter. We only care about if x is equal to 2. So basically, you can either come from the left side, or you come from the right side. So the way you say left side, you say lim as x approaches 2 from the minus, which means it comes from the negative side. So this is the negative side of the graph. It approaches this way, and then f of x over here, and then you ask yourself, what does it approach as f of x approaches 2 from this side? Who cares about this side? This side is useless for us. We only care about the left side. So if we're only looking at the left side, what thing does it approach? Let's say this is 5, and this is like negative 1. Then our f of x approaches 5. However, if we approach from the other side, it's completely different. So if we do lim from the right side, which is the positive side of the graph, right? Because as you go to the right on the x-axis, it becomes the positive. You basically get that x approaches 2 plus of f of x is equal to negative 1. Wow! Okay, very cool. But then, what is it if you do lim as x approaches 2 without any plus or minus nonsense? This is an easy way to tell whether a limit exists, okay? If lim of x approaches 2 minus and x approaches 2 plus are different, a limit does not exist. You cannot say that this exists. It's just impossible to tell because it approaches two different numbers. Which one is it? You don't know. So in this case, do not give an answer because you can't define the limit. But if they're equal to the same thing, then you know there is a limit. So this is a really quick way to check whether a limit exists at a certain point. Just do the left side, then do the right side, and see if they come to the same point. Alright, so one troll thing they might do is give you a table and ask you to estimate the limit. Now these ones are really easy if you know what a limit is, but I'll just do a quick example. So usually they give you like a table like this, and they give you the x coordinate, and then they give you f of x. So let's say they're feeling troll and they gave you lim of f of x as x approaches, let's say 69, let's go. So basically what they're going to do is they're going to give you like 68.9, then they're going to give you 68.99, and then they're going to give you the other side. But they're not going to tell you what it is at 69 because they're trolls and they don't want to tell you the answer. And then they do 69.01 and 69.1. And then once they give you these numbers, they will give you some values for f of x. And then from that, you have to determine what lim of f of x as x approaches 69 is. So let's say we take a beautiful red color, and then we do 121, 120.2, 119.9 or something, and then 117, sure. And as you can see, as you come from the right side, it approaches 120, right? And as you come from the left side, it approaches 120. So obviously, like, the limit here is just going to be equal to 120. I don't really know how to make these questions hard, because like you literally just see as it gets closer to the actual number, which should like fall somewhere here, you just take like basically what's in between here, what it should be approaching. So it's not that hard. Okay, and then I think this personally is the hardest part about limits is the limit properties, because those you actually had to do some manipulation and then you could solve the limit. So basically, like, it's literally just arithmetic, right? It seems simple. So obviously there are 4 rules for it, or actually there's 5. So obviously addition. So basically the first thing we got is we got lim of x approaches some number c of f of x is equal to some number L. How about that? And then let's say we have another function, lim of x approaches c of g of x, and that's equal to m. Dang. Then we can basically find a bunch of combinations of these functions. So let's say that we have to find lim of f of x plus g of x as x approaches c. Make sure that this c is the same, otherwise it's troll, because you can't apply like a limit at a different point to a limit at a totally different point. That doesn't work. So make sure that this c is the same all over here. So basically we could literally just split this up into like equal to L plus m, because you could kind of think of it as distribution, which is technically not, but like basically it's the same thing as taking the lim of f of x as approaches c plus the lim of g of x as that approaches c. And then you can do the same thing for f of x minus g of x. The lim of that as approaches c is just going to be L minus m. And then the same thing for multiplication and division. Now remember, the division one does not work unless the bottom side, the denominator, I totally know what the bottom side of a fraction is, that has to not equal 0, otherwise it doesn't work. And then the last one, I said there was 5, okay, don't worry, I know how to count. It basically said that lim of x approaches c of f of x to, like, let's say, what's a cool power, let's just say to the a. Then this is literally just equal to L to the a. So essentially what this just says is like you could plug in the values for the limits and just do the operation on those values and it should still come up to the same number. Be careful when you're using these because these don't always work. Like, I mean, it basically always works, but just make sure you're not having any like weird undefined stuff or zeros or infinities or anything. Like, for example, an infinity minus an infinity is not necessarily infinity or 0 or one of those two things. It could be somewhere in between. So you can't just always blindly apply these. So a common question that applies these formulas is basically like, it gives you 2 graphs. It gives you this graph over here, which we'll call f of x, and it'll have a nice little squiggly line, and it'll approach some value, and it'll be like that, let's say, and then this is 5 over here, and then I'll give you another graph. Wow, 2 graphs is crazy. And then I'll give you like this, and then I'll give you that, and then I'll give you like what? Like this thing. I don't know what I'm doing. Okay. And then this is like 5 over here. And then let's say that this over here is like -4. And then this is 2. And this is g of x. Okay. And basically the question is going to be like, okay, what is lim as x approaches 5 of f of x times g of x? Totally couldn't have seen that coming. Okay. Now we can immediately use our epic properties of limits, and we can basically say that this is equal to lim of x approaches 5 of f of x times lim approaches x, wait, what? Limit x approaches 5 of g of x. And then we literally just plug in and we get like what? We get 2, because here it approaches 2 from both sides, so it's not undefined. And then over here it approaches -4 from both sides. Very cool. Bro, this literally doesn't satisfy the vertical line test. Okay, I'm bad at drawing. I'm sorry. And then this is just gonna be -4, and our answer is gonna be -8. So that's like a common question. These are not that hard either, so you should be Gucci on these ones. But yeah, that's basically how you apply these addition, subtraction, multiplication, division, power rules. Now to spice, whoops-a-daisies. Now for the most part, you can find limits literally just by plugging it into the function. So like let's say that you have like limit as x approaches c of f of x. This is literally always equal to f of c, like generally for all normal functions, unless it's like weird and it has like asymptotes or jump discontinuities. But for a continuous function, this is basically true. So first try plugging it in, or well, okay. My personal take is that the easiest way to do it is to graph the function if it's not plug-inable. Because once you graph the function, you draw its asymptote, then you clearly know where there's like jumps or where there's discontinuities or whatever. And then like it's easy to find the limit. So like this is the best way to like try to solve it. But sometimes they like to spice it up and they like to give you like multiple functions. It's called a piecewise function, and it basically, you know what a piecewise function is, you better know what a piecewise function is. But let's do an example problem. Holy moly, that took me way longer than it should have, but I'm sorry. My neatness does not come okay, I'm sorry, this is not neat either, but it's pretty good for me, okay? Pretty good, okay? And that actually took some effort. But anyways, it's time to mark this boy up and ruin all my hard work with an epic orange, which is the color of the channel, even though I don't use this color at all. So basically they're using my epic strategy of finding the left and then the right and then the actual limit, because in order to find the actual limit, you have to know whether the left and right sides of the limit are equal. So, basically how we're going to do this is like, let us just think of this graph a little bit. So, if we draw it like this is our axes, we basically have that there's some function over here, I don't know how it looks, I don't feel like figuring out how it looks. Well, actually, okay. So, first thing we know is that it has an asymptote at x is equal to 1. So, there's like an asymptote boy over here. And then when it's slightly less than 1, this denominator is going to be negative, but the numerator is going to be positive. So the whole thing is going to be very, very negative. So it's going to go something like, not supposed to cross the asymptote line. Okay, so something like that. Okay, and then if you're slightly, okay, already messing this up, but if you're slightly greater than 1, the denominator is going to be positive, the numerator is going to be positive, so it comes down from here. And then this happens all the way to x is equal to 4. Okay, and then you know that the root function looks like something, but let us see what they're equal to at x is equal to 4. So if we plug in 4 over here, we get 6 over 3 is equal to 2. So this over here is going to be 2. And then if we plug it in here, whoa, it's also equal to 2. So basically, our graph kind of looks like that, because that's how square root functions look. Well, technically it's like something like that, but just to make it clear, we're just going to draw it like that. So if you look at the picture, this is like super obvious, right? As you approach from the left, like it just goes to 2. So this is 2. As you go from the right, go this way, it becomes 2. They're both equal, so it's 2. And then at 2, what is it equal to at 2? We literally just plug it in here. We get 4 over 1 is equal to 4. Very cool. Easy peasy, lemon squeezy. Now how the heck do you deal with absolute values? Let's say we have f of x is equal to x minus 3 over x minus 3. Now if you're a math geek and you already know all the math competition tricks, this is literally just like -1 for everything less than 3 and +1 for everything greater than 3. But you probably don't know that, so let us just figure out how this works. So whenever you see an absolute value, you have to break it up into where it's negative and where it's positive. So x minus 3 is negative whenever x is less than 3. So we can break this up into a piecewise function. So let's say that like x is less than or equal to 3, let's say. Or let's do less than 3 because we're cool. Over my less than or equal sign look like a less than sign, so I didn't even have to change anything. Wow! Okay, so if it's less than 3, the numerator gets negated because you want to have positive. So then you get 3 minus x, which is always positive, so we're good. So then it's going to be 3 minus x over x minus 3, which is just -1. -1! And then if x is greater than or equal to 3, then this just stays the same because it's already positive, so we don't need to change anything, and then it's just 1. Alright, so you have this, right? Then if they ask you limit problems about this, what is it when it approaches from the left? Okay, draw your diagram. It's way easier if you have a diagram. Okay, so you have this thingamajigger, then you have like x equals 3, and it basically goes -1 all the way here, hole over there, greater than or equal to 3, like that. So, if you look at the image, it's so easy. from the left as you approach 3 is what? It's -1. And when it approaches from the right side, it's just 1. Like literally, like just draw an arrow. Where does it go? It goes to 1. Wow. Wow. And can you define what the limit is at 3? No, you can't, because it approaches completely 2 different values. Alright, epic. We are zooming through this material. Alright, so like you probably know how to deal with these things already, but like the most obvious things that you have to apply limits to are functions with jump discontinuities. And usually they don't give you the graph every single time. They usually give you a function and you have to figure out the jump discontinuity. So pretty easy example, let's do it. So f of x, or actually let's do a hard example. So I am going to think of a question from the top of my head. Let's say x squared minus 4x plus 5, or no, minus 5, and then over x squared, minus 7x plus 10. Okay, and let's say we wanted to find the limit as f of x approaches, as x approaches 5, let's say. Now, whenever you're faced with a fraction of functions, of polynomial functions, it's so, like, there's literally, like, one way to solve them. Very unlikely there's going to be a different way to solve them. You just factor. Just factor, just factor, just factor. So easy, straightforward, stuff you gotta know. So basically, if you know how to factor, you'd probably be able to factor this. So it's x minus 5 times x plus 1 over, x minus 5 times x minus 2. And wait, could you cancel something out? Yes, you can. So we literally just cancel out this nonsense over here, and you are left with x plus 1 over x minus 2. And what do you do when you plug in an epic number? Okay, I kind of skipped a step, but like, because you're cool, the first thing you try is plugging in the number into the function. And if you try to plug it in, you get 0 over 0, which is nonsensical, pretty useless, no need to worry about that nonsense. However, if you cancel out the x minus 5 and you plug it in, you get something nice. You get 6 on the numerator, you get 3 on the denominator, and what do you get? That's right, you get 2. Alright, and because you had to cancel out the x minus 5 and it's not defined as x minus 5, you have a jump discontinuity there. So if we wanted to draw the graph of this, which is always a good idea, like if the one thing you want to practice for solving limit problems, just practice drawing the graphs, because if you can draw the graphs, you automatically get the limit answers. Alright, so basically everywhere other than x is equal to 5, let's just make sure you mark that out, it's going to be defined. Okay, well I mean, other than x is equal to 2. And basically what we want to do is we want to mark out the important x coordinates, so basically when each of these terms are 0. So 5 we already got, we got to do 2, and we got to do -1. So basically at -1, this whole thing is equal to 0, and it's not undefined 0, it's actually 0. So we know it has to intersect the x-axis at that point. And then as this gets really negative, the numerator and the denominator are both negative, so it comes like from some positive infinity over here, it goes through there, and then at -2. So let's say you're slightly less than 2. Then the numerator is going to be negative, but the wait, what was I saying? The denominator is going to be negative, but the numerator is going to be positive. So, in that case, it approaches negative infinity as you approach this asymptote. On the other side, though, the denominator is going to be positive because slightly greater than 2 minus 2 is positive, and then 2 plus 1 is also positive, so it comes from positive infinity. And then it goes over here, and what does it approach as it goes to infinity? Now, I'm just going to bring in this cool trick right here. Basically, if you have polynomial over polynomial, the limit as you approach infinity is just going to be the ratio of the front number. Basically, the way you could think about this is like, if you have a really big number, right? If you square it, that's going to be like massive, okay? And if you like to the cubit, that's like super massive. So basically, when you go to infinity, you could literally just eliminate the other terms. And then basically the ratio of the coefficients is the only thing that's left. And that's how you remember that only applies when you're doing to infinity. So in this case, the to infinity ratio is just going to be 1, so it'll approach some asymptote, horizontal asymptote of 1. Okay, so we got our very epic, what do we have? What is this epic thing? Very epic graph, and from this it's pretty clear that this limit is 2, and then like if we approach 2 from the left side, it goes to negative infinity, and 2 from the right side, it approaches positive infinity, and as we go to negative infinity, it goes to positive infinity. We all got that all just by drawing the graph. Super fast. Alright, another common thing is rationalizing the denominator in order to solve these problems. So let's say we have f of x is equal to like x minus 1 over root x plus what? X plus 3 minus 2. How about that? And let's say we wanted to evaluate the limit as this thing approaches, let's see, limit as x approaches 1 as of f of x. Okay, now basically whenever you see a irrational thing in the denominator, you should always try, okay, well, a very good math problem solving strategy is to try everything you possibly could. And if you see irrational things, you should try to rationalize it. Like, even if it's in the numerator, you could try moving it to the denominator by multiplying by the conjugate. So that's one of the things you should always try in a math problem, or like calc problem that involves irrational stuff. So in this case, if we try to rationalize the denominator, we basically get x minus 1 times root x plus 3 plus 2 over, it becomes difference of squares, so it's going to be this squared, which is x plus 3, minus 2 squared, which is minus 4. And we should draw parentheses. Okay. And then this is literally just equal to, the denominator becomes x minus 1, so wow, we could cancel stuff out. And this becomes x plus 3 plus 2. Holy moly, now we can actually plug in this nonsense. Bro, I keep forgetting, but first step, I already knew that it's not gonna work if you plug in 1, but first step, you should always try plugging it into the original function. But in this case, it becomes 0 over 0, so it doesn't work. But now we can plug in and we get 1 plus 3, root of that is 2, plus 2, 4. Noisu. But anyway, that's like showing you the power of expanding, factoring, whatever you want, rationalizing. Those are the basic three categories: expand, factor, rationalize. Alright, one cool thing that I don't know how applicable it is on the AP exam is the squeeze theorem, but like my teacher went on about it. Bro, that guy went on like a whole class on the squeeze theorem. It's kind of cool, but just don't know how applicable it is. But we're just going to cover it real quick. So basically, like, let's say that there's a function and you don't know how it looks. It's just some squiggle on a paper, you don't know what it looks. Just kidding. You don't know how the function looks and you're trying to find a limit of the function. Well, let's say that like you have two functions that are just going wee. No, that's not a function. I'm having too much fun with this. God dang it. But let's say that you're having a function and it approaches this number, and then there's another function that goes like that, and then like that, and then like that. Okay. Now let's say that we know that this is like f of x and this is g of x, and we know that the function that we want to find is like h of x. And let us say that we know that h of x is less than or equal to f of x, but it's also greater than or equal to g of x. Then we know that it has to fit somewhere in between here, right? Because if it was over here, it'd be greater than f of x. If it was over here, it'd be less than g of x. God dang it, this function needs to be a sandwich. But anyways, the point is, like, let's try to draw this function, okay? We can have fun however we want. We can be anywhere we want. Okay, we can't violate the vertical line test, which I have been doing quite commonly, but what we can't do is we can't go anywhere here. We're forced into a single position. So, like, we don't know anything about where it has to be out here, but over here, let's say this is x is equal to 5, we know that the limit as this function approaches x is equal to 5 is literally equal to whatever this y coordinate over here is. Like, there's no other option. So basically, that's what the squeeze theorem says. Alright, so we're almost done. Now we gotta talk about discontinuities, continuous intervals, and lastly, we gotta talk about quotients, I think. And then intermediate value theorem, and then we're Gucci. So, that's actually quite a lot. But don't worry, we're gonna get to it. Discontinuities are pretty straightforward. So, like, the first one you got is, like, obviously your point, which we've talked about already. You got like that. Okay. Like, or it can even be there, like, there could be a point there. And this is basically called a point or removable discontinuity. And it's, like, pretty easy to recognize, right? Like, literally, there's one point that's missing and is not, like, continuous with the rest of the function. Then, of course, there's a jump discontinuity. And that kind of looks like this, right? You got this over here. However, it doesn't continue from there. It, like, starts at some completely random point and then it goes like that. Okay. And then, like, another obvious one is the asymptotic one. And, as you might expect, it has an asymptote, so it's not continuous. Like, it goes like that. So, at, like, this point over here, it's not defined, so it's not continuous. Like, it doesn't, there's no where these two are connected. Alright, just memorize that. It's not that hard. I don't even know, like, probably not going to be asked on the AP exam, but it's there. Alright, and because we are math geeks, we are going to talk about what the definition of continuity is. It basically means that lim as x approaches c of f of x is equal to f of c. This, that's not how you write it, c. Actually, no, that's how I write it, c. But anyway, this is a bare bones definition of continuity, and basically it can't fail you, okay? It basically means that at any point, if it approaches one thing at that point, like from both sides, it has to be equal to that thing at that point. It can't just like approach here but then suddenly be over here. Okay, that doesn't work. So in order to be continuous, well, you can probably just tell by looking at it whether it's continuous, but yeah, yeah, this is just the definition. It's kind of helpful. But the tricky part are the intervals, okay? So like if you have a comma b like that, then it's kind of easy, okay? Because then you basically just need to have it continuous on the interval. So like for example, if you have a function like this and it's like this and it has a hole over here, continuous over here, and then it has another hole over here. This is A, this is B. Then it's continuous over the interval because it doesn't really matter what it is at like A and B because this is an open interval, so it doesn't include A and B, so it doesn't have to be equal to anything at A or B. But it gets annoying when you have it closed like this, because then it actually has to be defined at A and B. So basically a hole is not going to work on a closed interval. So you have to have these filled in for this to work. So don't get trolled by that on the AP exam. That exists, so just know about that. And then a cool thing you could do if you have a if you know that something's continuous on an interval, you can apply Intermediate Value Theorem. And basically what that says is if you say that like this point over here is like 3 and then this endpoint is 2, then basically what the Intermediate Value Theorem says is that the function has to hit every point in between 3 or 2, okay? Like let's say you have 2.5, you can't like never hit 2.5, okay? Let's just say that this is y is equal to 2.5. There's no way that this function can reach to 2 without going through 2.5. That just doesn't make sense. You want to try drawing a function that goes like that? Okay, so we're not gonna touch it. We're not gonna. Oh, wait, it worked. What? Okay. Lifting pens are kind of OP. Okay. But anyway, the point is, like, for any, like, y coordinate between 3 and 2, you can't not pass through it if your function is continuous on this interval. Now, when I took the calc exam, like, they had multiple choice, right? So they did have questions on the IVT, like, what can you infer from the IVT? And then they give you, like, 4 options that were kind of stupid, but it's okay. I don't know how they're going to ask it in a completely short answer format. I don't know how it's going to work. But yeah, so just know what the Intermediate Value Theorem says. Like, if you know the logic behind it, like it's really obvious what the logic is, like you have to pass through every point in between, then it's going to be pretty easy for you. Alrighty, last but not least, we got infinite quotients and then we are done. Let's go. So let's say we have lim as x approaches infinity of, like, let's say f of x over g of x. So some of the obvious things are like, basically if f of x is defined and g of x is defined and not equal to 0, then this is obviously just going to be lim of f of x over lim of g of x. Okay, we already learned that. Okay, so the cases, infinity, 1. 1 just means finite, okay? This is going to be equal to, what's it going to be equal to? It's going to be equal to infinity. Okay, if you got 0 and you got 1, then this is also going to be equal to 0. Then if this is like 0 and infinity, also going to be 0. If it's 1 and infinity in the denominator, then it's going to be 0 as well. Because, like, if you have like finite number divided by like a really big number, it's going to be 0. Then if you have infinity over 0, it's basically just going to be infinity because you're basically taking a really big number, dividing it by a really small number, which is just going to make it even bigger, so it's just going to be a really big number. Now be careful with like positives and negatives, because like if g of x approaches 0 from the bottom, like if it's negative 0, like it becomes a really small negative integer, then it's going to approach negative infinity. So be careful with your signs, that is the thing. Now in this chapter, like in this unit, they don't teach you how to deal with like 0 over 0 or infinity over infinity, so I wouldn't worry about that just yet, because you're going to learn something epic called L'Hopital's. Well, you probably should have already learned that, but L'Hopital's is used for those things. But basically, like the easiest way to deal with quotients is just think of it as really big numbers and really small numbers. So if you divide by a really small number, it's going to be a really big number. If you multiply by a really small number, it's going to be a really small number. If you divide by a really, really big number, the overall result is going to be a really small number, and basically think of it as big and small numbers. That's the best way to think about it. That's how I think about it. There you go. And basically that's everything that's covered in the limits and continuity chapter. I will continue on the next video with Unit 2. Basically how we're going to do this is we're going to alternate with chem. It's going to be epic. Alright, thank you guys for watching. As always, if you enjoyed the video, leave a like and subscribe for more, but this was a trial run. You guys need to tell me what I need to do better, what you guys want more of, what you guys want less of, and we should be good. Suggest it in the comments. Thank you guys so much for watching again, and see you guys next time.